Learn about resonance. And what resonance is the movement of electrons between a single and a double bond on equivalent bonding pairs that are right next to each other. So that sounded like a lot, but what I actually mean, well, we'll look at the example carbonate and we'll look at what I actually mean. So carbonate is CO3 and has a -2 charge. Two of the oxygens have gained electrons, become negative, and they're singly bonded to the carbon. And then you have one oxygen that's got its standard double bond that would occur if it hadn't gained the electrons. So what you have here is a single bond right next to a double bond. And carbon to oxygen in both pairs is equivalent. So what can actually happen is there's no reason that this oxygen gained the electrons and the other oxygen didn't. So what can actually happen is those electrons can flow back and forth between here, here, and they end up moving all around to form these different resonance structures. So just to show you one example of the motion of these electrons, using a different colored marker. You can take one electron pair from here on the negative oxygen and dump them into here to form a second bond, or a pi bond. And what would happen then is the carbon would become overcrowded with electrons, and it would kick out one of those bonds into being a third unshared pair on that oxygen atom. And that would result in this resonance structure, which is stable. Also, I mean, now there's no reason the electrons are fixed in those positions, so electrons from here can drop down here and then kick those out, and then you have this structure. So the electrons essentially move around all over the place, and they really spend an equal amount of time in each of the positions, and therefore all three of these resonance structures of carbonate are equivalent and likely to happen. Acetate's another example of a molecule with that. Not quite as much movement, but you have both of these structures would be considered valid. It's an anion, so it has a negative charge. One of the oxygens negative charge with a single bond, then you have your double bond to a neutral oxygen. And what happens is those electrons, like the same way, can drop down, form the double bond here, and then the electrons can kick up to form a single bond there, and the negative charge would shift with that as well. So these are two resonance structures for acetate, but really what happens is the electrons spend their time equally between each atom, and you end up with like a 1.5 bond order between each of them. So the electrons move around, and it's happening all the time. Another common example of a molecule that has a lot of resonance exhibited is benzene. It's a very common, it's a whole branch of chemistry having to do with aromatic compounds, and it actually gives the sweet smell to gasoline. Doesn't mean you should drink it. So you have, in the molecule, you have alternating single and double bonds between all the carbons. And what can happen is, just like we showed earlier, I'm not going to draw it out for this one because then it would just become a catastrophe, but basically you can go back and forth between these two resonance structures as all the single bonds then become double and all the doubles become single. But what really happens is you have sigma bonding occurring between all of the carbon atoms. I didn't draw the hydrogens in just for clutter purposes, but they're on each carbon. And then I drew the unhybridized p orbitals, which for each carbon would, initially have one electron. And what will happen is, at first you would have bonding between these p orbitals, and you would end up with this structure right here. But really these electrons are all moving around in this giant circle, forming both of these at all times, really, going back and forth. So really what you end up with is this circular ring of electrons in benzene, which gives it a nice level of stability for that molecule. So resonance, you don't need to know all of this, but what resonance is the shifting of electrons between equivalent adjacent bonds.